This video is going to talk about the physics of rolling. Why do objects naturally roll down an incline? Up until this point, when we've talked about motion on an incline, we thought through the forces on an object. So let's say we have a block on a smooth surface, so friction is negligible. Feels a gravitational force down. The normal force is always pushing up perpendicular to the surface. In this case, if there's no friction, the block's going to naturally accelerate down the incline parallel to the surface, because when we add up all the forces on the block, what's left over is the x component of gravity. Even if we had a ball or a disc on a frictionless surface, it would similarly accelerate in the x direction because of the x component of gravity. So why do objects roll down inclines? It's because friction is significant. When friction is large enough to prevent sliding, a ball or a disc pivots at the point of contact with a surface. And so where it makes contact with a surface, friction is large enough to prevent sliding, but it can't prevent rolling. Well, if something starts not spinning or not rolling, and then it begins to, that means it's going to have an angular acceleration. So this disc is going to accelerate angularly in the clockwise direction. And why does anything have an angular acceleration? It's because all the torques, when you add them up, aren't balanced. So what are the torques on a disc or a ball when it's on an incline? Well, there's three forces. We have the gravitational force pulling straight down, acting at the center of mass of the disc or the ball. And then we have the normal force of the surface pushing up perpendicular to the surface. And friction is significant, and the ball would tend to slide down the ramp, and so that means friction has to be pushing parallel to the surface up the ramp. So do those things exert torques? If we add up all the torques or potential torques, what do we get left over? Well, there's potentially the torque caused by gravity, the torque caused by the normal force, and the torque caused by the frictional force. And torque exerted by a force is the size of that force times the radial distance that force is applied from the pivot point, and then we multiply by the sine of theta if they're not perpendicular. So what about gravity? Well, if this is the pivot point and gravity's acting at the center of mass location, the radial distance vector from the pivot point to the force application is r. And there's an angle of theta between the radial distance vector and the gravitational force, and these two things are not perpendicular, so we have to use rf sine theta to figure out the torque. So the torque caused by the gravitational force is that radial distance vector, which is just the radius of the disk, times the weight of the disk, the gravitational force, times the sine of this angle between those two things. So it's r mg sine theta. Mg is just the gravitational force. And why is it negative? The gravitational force is exerting a clockwise torque about this point. It's trying to make the thing rotate in the clockwise direction, and that's our negative rotational direction. So gravity causes a negative torque on the disk. What about the normal force and the frictional force? Well, notice both the normal force and the frictional force are exerted at the pivot point location. They don't have any radial distance. If they're exerted at that pivot point, in both cases they exert zero torques on the disk. So when we add up all of these torques on the disk, we see the only thing left over is the negative torque caused by gravity. So we say, why do things roll? Well, the torque exerted by gravity causes an angular acceleration, alpha, which increases the disk's angular velocity as it moves down the ramp. So gravity causes a torque, therefore there's an angular acceleration, therefore things will spin faster and faster and faster while they move down an incline. And if they're spinning faster and faster and faster, they're also moving down the incline, so their center of mass is also moving in the translational direction. It's accelerating translationally and it's accelerating angularly. Let's think through a situation where a disk rolls down a hill, across a flat horizontal surface, and then up an incline. We already know that the disk on the left-hand side here is going to accelerate in the negative angular direction because it's feeling a negative torque from gravity. And if there's a negative torque, that's going to cause a negative angular acceleration. And how do we think about what is angular acceleration? Remember, angular acceleration is just the change in angular velocity per unit time. So if you have a negative angular acceleration, your angular velocity will be changing negatively as time goes on. So if we make an angular velocity versus time graph, if we start with an angular velocity of 0, in this first region, if this sphere has a negative angular acceleration, that means the angular velocity is going to get more negative as time goes on. And it's going to do that in a linear way because the angular acceleration is constant. Why? Because the sum of the torques is constant. Why? Because the torque caused by gravity is also constant. So what's happening on the horizontal surface? This thing is spinning. It does have an angular velocity in the negative direction, and it is moving translationally. But we know there's a gravitational force acting down from the center of mass. We know the normal force of the surface is pushing straight up, perpendicular to the surface. The question is, this is a rough surface, but is there a frictional force? Well, in this case, gravity is now pulling straight down. It's parallel with the radial distance relative to the pivot point, so gravity is not exerting a torque. The normal force, it's also not exerting a torque. And so these two forces are not trying to make this thing spin faster and faster in the clockwise direction or slow down in the clockwise direction rotationally. And so when this thing makes contact with the surface, the surface of the disk, once it gets to this point, it's not trying to spin faster and faster, so it's not tending to slip in any one direction. So there's actually no frictional force when something is rolling at a constant angular velocity. Even if it's a rough surface, there's no frictional force. And so in this case, if we add up all the torques based on gravity and the normal force, there is no net torque. Therefore, when we think about the angular acceleration, there's no net torque, there's no angular acceleration. That means there's zero change in angular velocity. So the disk already had a negative angular velocity. It's going to keep that same negative angular velocity from time 1 to time 2, the whole time it's on the flat horizontal surface. And then what about when it's going up the incline? Well, let's throw all three of our forces on there. We've got our gravitational force pulling down, our normal force pushing perpendicular to the surface. And in this case, gravity is exerting a positive torque on the system. It's trying to make this thing now rotate in the counterclockwise direction. That's a positive torque. And if it's doing that, it's going to be decreasing its angular velocity. And if this thing is going to start slowing down a little bit, that means the disk is going to tend to slip forward. Therefore, friction is going to be in the negative direction. Since the torque caused by gravity is positive, that's going to lead to a positive angular acceleration, which is going to be a positive slope on an angular velocity versus time graph. So if it was spinning in the negative angular direction, and now the torque is positive, the slope of this graph has to be positive. The angular velocity has to get less negative as time goes on until eventually, once it gets high enough, it'll stop spinning altogether, and then it'll actually start rolling back down in the other direction. So now let's make one little change. If instead of going up a rough incline where friction is significant, let's imagine there's insignificant friction on a smooth, let's say an icy surface. If that's the case, the frictional force goes away, and this thing's going to slow down. Translationally, it's going to decrease speed as it moves up, but it's not going to change its angular velocity. When there's no friction, this thing is not going to pivot about the point right here. It's just going to slide, and therefore this thing will keep rotating at the same angular velocity. There's no opportunity for gravity to exert a torque on the sphere because it can't pivot about that point. It's sliding. So the net torque is zero. Therefore, the angular acceleration will also be zero in this region going up the ramp. And so if it has a negative angular velocity, it's going to keep that same negative angular velocity. Well, what does that mean? That means this disk is going to move up the incline. It's going to slow down translationally. The center of mass will decrease speed, but it will not change its angular velocity. It'll just keep spinning in the same clockwise direction at the same rotational speed. The last thing we're going to talk about is just a little quick comparison between a hoop rolling down an incline and a disk rolling down an incline. And let's imagine both of these things have the same mass and they have the same radius. We're going to release them from rest on the same angle incline. And let's just think about how we would compare the rotational motion of each and the translational motion of each. So we're going to compare aspects of the rotational motion part of the disk and the hoop's motion and the translational part of the motion. So starting with the rotational motion, both of these things we're going to start from rest, so they're going to start not spinning. Their initial angular velocity will be the same. It'll be 0 radians per second. And then what's the sum of the torque? Well, the torque comes from the gravitational force on both the hoop and the disk. Since they have the same total mass, they're in the same angle incline, they have the same radius, they're going to feel the same size torque caused by gravity. So, and the normal force and the frictional force don't exert torque. So the sum of the torques are the same, and it's just equal to the torque caused by gravity on each, which is the same size. Well, what about the rotational inertia of the disk and the hoop? And the rotational inertia depends on the total mass of the object and how far away that mass is, or each part of the mass is, from the center of mass location. With the hoop, all of that mass, assuming a thin hoop, is basically at the full radial distance. With the disk, some of that mass is at the full radial distance, but the rest of it, if it's evenly distributed, gets closer and closer and closer. So that if we add up all of that, the m times r squared values, that means the disk has less total rotational inertia than the hoop. It's going to resist angular acceleration less. And if we're thinking through the angular acceleration, that comes from our Newton's second law equivalent equation, where it's the angular acceleration is equal to the sum of the torques divided by the rotational inertia. And if they feel the same size net torque, but the disk has a smaller rotational inertia, that means it's going to experience a larger angular acceleration. It's going to increase its angular velocity at a greater rate. And then the angular displacement, they're going to be on the same incline, so they're going to spin through the same number of radians where they start to the bottom of the ramp, and so the angular displacement will be the same size. When we're thinking through the translational part of the motion, we have a couple equations that help us go between the rotational motion part of an object and the translational motion part of the object. So if we know the angular displacement, we can figure out the linear displacement. We know the angular velocity multiplied by the radius of the thing spinning, that will give us our translational velocity. And if we have the angular acceleration, that can give us our translational acceleration. So these will help us compare these things. So initially, they both start from rest, so they have a 0 initial velocity. And then the translational acceleration, this one's a little tricky. So let's go back to what we know about the angular acceleration and how these two things are related. The disk has a larger angular acceleration, and angular acceleration is just the radius times the angular acceleration, or r times alpha. R is the same. Alpha is greater for the disk. Therefore, the disk is going to have a larger translational acceleration. It's going to increase its speed at a greater rate as it moves down this incline. Well, if they're moving down the same incline, they're going to have the same displacement. The disk and the hoop will travel the same linear distance. So the last thing we're going to compare is the time it takes the disk to reach the bottom and the time it takes the hoop to reach the bottom. And let's just go off of the translational part of the motion, how they're moving linearly. They're both going to be displaced the same amount. They're going to move the same amount down the incline, but the disk is going to have a greater linear acceleration than the hoop. Therefore, it should take the disk less time than the hoop because it has a larger linear acceleration, because it has a larger angular acceleration. And that's something we can compare. So here we go. We have our disk and our hoop starting from rest, moving down the same angled incline from above and from the side, and we can clearly see the hoop takes more time to reach the bottom. The disk takes less time, just like we predicted. I hope this has been a helpful introduction to why objects roll down inclines and how to think about the rotational part of the motion and the translational part of the motion. In a future video, we'll talk about the energy considerations and how to actually predict how fast something is going when it starts from rest and rolls down an incline.